Hello students, in the last class we have studied about the UPAC nomenclature of coordination compounds. In that we have studied UPAC nomenclature of anionic complexes, cationic complexes, nomenclature of neutral complexes, and the nomenclature of coordination compounds with a bridging ligand and ambidentate ligand. In the today's class, we are going to study about the important topic, that is effective atomic number. Okay, effective atomic number theory was given by Sidgwick. Effective atomic number theory was given by Sidgwick. He suggested that central metal ion accept the pair of electrons from the ligands until EAN means effective atomic number of central metal ion becomes equal to the atomic number of succeeding inert gas. Okay, ಏನು ಮಾಡುತ್ತೆ central metal ion? It accept the electrons from the donor atoms until metal atom in the complex ion attains the effective atomic number which is equal to the atomic number of succeeding inert gas. Okay, here ligand donates electron space to the central metal ion to form coordinate bond. Ligands donates electron space to the central metal ion to form a coordinate bond. The number of coordinate bonds depends upon the number of vacant orbitals. Okay, number of coordinate bonds depends on the number of vacant orbitals in the central metal ion. Okay, when the coordinate bond is formed, this bond is semi-polar in nature. The coordinate bond is semi-polar in nature, in which electrons are donated by one ion or a molecule. Okay, here only one ion donate electrons to the other, therefore the bond is known as semi-polar bond. Okay, Sidgwick extended the Lewis concept. He also used the Lewis concept to explain the formation of coordination compound. Here metal is a Lewis acid and the ligand is a Lewis base. This is about the Sidgwick's theory of effective atomic number. Then what is effective atomic number? Effective atomic number is the sum of electrons. Okay, here effective atomic number is the sum of electrons on the metal ion plus electron donated by the ligands. That sum is called as effective atomic number. The sum of electrons on the metal ion and the electrons donated from the ligand is called as effective atomic number. This is the definition of effective atomic number. Then how to calculate the effective atomic number and what is the importance? As we can say, effective atomic number of a metal ion is a sum of electrons on the metal and electrons donated by the ligands. In general, we can say that, or according to the Sidgwick's theory, En of metal, effective atomic number of metal, is equal to the atomic number of next inert gas. Effective atomic number of metal is equal to the atomic number of next inert gas. Okay, next inert gas means in the 3D series the inert gas is krypton, and in 4D inert gas is xenon. In the 5D series the succeeding inert gas is radon. That An is equal to the atomic number of succeeding inert gas. It is calculated by using the formula An is equal to Z minus X plus Y. An is equal to Z minus X plus Y, where Z is atomic number of the metal and X is number of electron lost during the formation of metal ion from its metal atom. Z is atomic number of the metal, X is number of electrons lost during the formation of metal ion from its metal atom, or it is nothing but the charge carried by the metal ion. And Y is number of electrons donated by the ligands. Y is number of electrons donated by the ligand. Okay, examples to calculate the effective atomic number. In the first complex, CuNH3,4SO4, tetramine, copper 2 sulfate, the UPAC name is, and the central metal ion is copper. The charge carried by the copper is 2 plus. Okay, therefore Z is atomic number of copper, that is 29, and X is number of electrons lost in the formation of Cu2 plus, or it is nothing but the charge on the metal ion. The charge on the metal ion is 2, therefore X is equal to 2. And Y is the number of electrons donated by the ligands. The ligand here is ammonia. It is a unidendate ligand. Each ammonia donates one pair. Therefore, total 4 ammonia are there. Therefore, 4 into 2, 8. 8 is the value of Y. Substitute these values in a EAN equation. That is, EAN is equal to Z minus X plus Y. EAN is equal to 29, that is atomic number, minus 2, the number of electron lost or the charge on the metal ion, plus 8. 8 is the electrons donated by the ligands. Therefore, EAN number is equal to 35. Okay. Copper comes in the 3D series. The succeeding inert gas in the 3D series is krypton. Its atomic number is 36. But we are getting the EAN value 35. Okay. EAN is not equal to the atomic number of krypton. Therefore, according to Sidgwick, this complex is unstable, or this complex do not obey the EAN rule. Okay, next you can see the second complex, COEN twice Cl2 Cl. EN is ethylene diamine. Ethylene diamine is a bidentate ligand. Bidentate ligand means each EN donates 2 pair of electrons. Okay, central metal ion is CO3 plus. Atomic number of the cobalt is 27. X is the number of electron lost or a charge on the metal, that is 3, and Y is equal to 2 into 4. 2 ethylene diamine. Each ethylene diamine donates 2 pair, therefore 2 into 4, plus another ligand is chloride ion. It also donates 1 pair, therefore 2 into 2 is equal to 12. Substitute these values in the effective atomic number equation, that is EAN is equal to Z minus X plus Y. EAN is equal to 27, Z value is 27, minus 3 plus 12 is equal to 36. Okay, we are getting the EAN value 36, which is the atomic number of krypton, that is a succeeding inert gas in the 3D series. Therefore, it obeys the EAN rule. Cobalt ion obeys the EAN rule. Next example, K3FeCN6, potassium hexacyanoferrate. Central metal ion is Fe3 plus. Atomic number of the Fe is 26. And the charge on the Fe is 3. It has 6 cyanide ions. Therefore, Y is equal to 2 into 6, that is equal to 12. Substitute these values in a EAN formula. Therefore, EAN of Fe3 plus is 26 minus 3 plus 12, that is 35. EAN value of Fe3 plus is 35. Okay. Succeeding inert gas in this series is krypton. Krypton's atomic number is 36, but we are getting the EAN value of Fe3 plus as 35. Therefore, it also do not obey the EAN rule. Okay, by this calculation we can say that all the metal ions which form the complexes need not obey the EAN rule. Okay, some complexes obey the EAN rule and some will not obey the EAN rule. Next, for example, complexes like, you can see the complexes AgNH3 plus, AgNH3 plus. Okay, here coordination number of the silver in the first complex, coordination number of the Ag is 4. In the second complex, coordination number of the Ag is 2. In this, the first complex, The first complex obey the EAN rule, but it is unstable. But the later second complexes do not obey the EAN rule, but the complex is stable. Therefore, EAN or Sidgwick's theory fails to explain the stability of the complex ions. Then what is EAN rule? EAN rule says that a metal ion continues to accept the electrons from the ligands till the total number of electrons present around the metal ion in the complex becomes equal to the atomic number of the next noble gas atom. EAN rule says that metal it is continue to accept the electrons pairs from the ligands until the atomic number of EAN is equal to the atomic number of next inert gas or noble gas atom. This is the definition of EAN rule. A metal ion continues to accept electron pairs from the ligands till the total number of electrons around the metal ion or EAN becomes equal to the atomic number of next noble gas atom. This is the EAN rule. When EAN of the metal ion equal to the atomic number of the next inert gas, then the complex is said to be more stable. The complex which obeys the EAN rule. The complex which obeys the EAN rule is said to be the more stable according to the Sidgwick's theory. Okay, in the periodic table we can see in the 3D series. This is the 3D series. The succeeding or the next inert gas here is krypton. Its atomic number is 36. Okay, when the EAN value of the complex ions of the 3D series becomes equal to 36, then the complexes are more stable. Okay, in the 4D series, the succeeding noble gas is xenon. It means the EAN should be equal to 54. Next, in the 5D series, succeeding inert gas is radon. Its atomic number is 86. It means the effective atomic number of elements of the 5D series should be equal to the 86. Otherwise, they are unstable. Okay, here are some of the examples which obey the EAN rule. First complex is CONH363+. Central metal ion is cobalt. Cobalt's atomic number is 27. Cobalt is in a +3 state. Therefore, number of electron lost 3. Therefore, 3. We get a 24 plus Y. Y is the atomic number of electrons donated by the ligand, that is 12. Total we get 36. EAN is equal to the atomic number of the krypton. Therefore, this complex obeys the EAN rule. Similarly, second example, platinum NH364+. Atomic number of the platinum is 78. Platinum is in a +4 state. Therefore, electron lost 4. Electron donated 12. We are getting 86. Okay, it belongs to 5D series. The succeeding member inert gas is radon. Its atomic number is 86. We are getting the EAN value also 86. Therefore, it also obeys the EAN rule. Next complex, FeCN64-. Atomic number of Fe is 26. Electron lost 2. Electron donated by the ligands 12. We are getting the EAN 36. This is the atomic number of krypton. Therefore, it also obeys EAN rule. Next complex, CrCO6, carbonyl ligand. Atomic number of the chromium is 24. Carbonyl is a neutral ligand. It don't have any charge. Neutral ligand. Therefore, chromium is in a stable oxidation, that is 0. Oxidation state of the chromium is 0. Therefore, 24 plus electrons donated by the carbonyl is 12. This is equal to 36. EAN is 36. This is the atomic number of krypton. Therefore, it also obeys EAN rule. Similarly, cadmium. Atomic number of the cadmium is 48. Cadmium is in +2 state. Therefore, 2 ligands, number of electrons donated by ligands 8. En is equal to 54. This is the atomic number of xenon. Therefore, this complex also obeys the EAN rule. Next, these are the complexes which do not obey the EAN rule. Example, NiCN4 2-, atomic number of the nickel is 28. Electron lost, or Ni is in a +2 state, therefore electron lost 2. Electrons donated by ligands 8. EAN value is 34. EAN value is 34, but the atomic number of the krypton is 36. Therefore, this complex will not obey the EAN rule. Next one, chromium NH363+, atomic number of chromium 24, minus electron lost 3, electron donated by ligand 12, EAN value is 33. This is also not equal to the atomic number of krypton. Therefore, this is also unstable and do not obey the EAN rule. Next, AgNH3+, atomic number of silver 47, minus electron lost 1, number of ligands or electron donated by ligand 4, in total EAN is equal to 48. This is also not equal to the atomic number of xenon. Therefore, it will not obeying the EAN rule. Similarly, next one, platinum NH3 2+, atomic number of platinum 78, electron lost 2, ligands donates 8 electrons. We are getting the EAN value 84. Atomic number of radon is 86. Therefore, EAN is not equal to 86. Therefore, it will not obey the EAN rule. Similarly, next one, FeCN6 3-, atomic number 26, minus electron lost 3, electrons donated by ligand 12. Therefore, EN is equal to 35. This is also not equal to 36. It will not obey the EN rule. The last one, vanadium CO6, atomic number of vanadium 23. It is in a neutral state. Therefore, charge on the vanadium is 0. 23 minus 0, 23. Electrons gained by or donated by ligands 12, 35. This is not equal to 36. Therefore, it will also not obey the EAN rule. These are the sum of the complexes which will not obey the EAN rule. Then what is the importance of EAN rule? EAN rule helps to explain the magnetic property of the complex ion. EAN rule helps to explain the magnetic property of the complex ion. The complex ion whose central metal ion obey the EAN rule are said to be diamagnetic, and the complexes which do not obey the EAN rule are generally paramagnetic in nature. Okay? By this way, we can explain the magnetic properties of the complex ions based on the EAN rule. This is about how to calculate the EAN and what is EAN and what is EAN rule. In the next class, we are going to study about the isomerism, structural isomerism and optical isomerism. Thank you.